Hello, I'm Yanqiu Ruan from Singapore University of Technology and Design, SGTD. The title of our work is A Nonparametric Approach with Marginals for Modeling Consumer Choice. It is a joint work with my advisors, Xiaobo and Karthik and Karthik Natarajan. First, let me introduce the background of consumer choice. Suppose that a retailer has a set of available products. They may offer different subsets of products for the customers, which are called the assortments. Customers come either to choose their favorite product from the assortment or leave without buying anything. The assortments may be different over time, from which the retailer can obtain the transaction data. That is the sales fractions across a collection of assortments. We describe the choice data in a journal form as shown on the left-hand side. We have M products, M assortments, and the sales fraction of each product in each assortment. Here, we choose the leave option as a product that is always available for customers. Discrete choice models are used to describe the demand. Given the observed choice data, the modeler can use the chosen choice model to describe the choice probability of a product I in every given assortment S, which is denoted as PIS here. As you can see, the specification of the choice probabilities depends on every product in every possible assortment, so it is high-dimensional. A model offers a simplification is the classical multinomial log MML model. The choice probabilities under MML are in closed form, which makes it widely used in different areas. However, the MML model is known to be quite restrictive. A popular model at the expressive end is the random utility model RUM. It can model any rational choice behavior. However, it is strong in Jagbathula and Resmarinchintan 2019. Verifying whether the observed choice data is consistent with the RUM family is intractable. Some parametric subclasses can offer a balance between representational power and tractability. However, there is a risk in model misspecification with parametric classes. Therefore, our goals in this talk are to identify choice models that can, first, offer a balance between richer representational power and tractability, and second, allow robust data-driven procedures for estimation, which does not require prior parametric assumptions on the model. One of the models meeting the two goals is the marginal distribution model, MDM. I will give an introduction to this model shortly. To check whether MDM meets the first goal, we begin by starting the question that, given the choice data across a collection of assortments, can MDM represent the choice data? In other words, we are asking what are the necessary and sufficient conditions for the observed choice probabilities to be recreated by MDM. From such conditions, we will see whether the set of MDM representable choice probabilities are reached or not, and we will also see whether checking these conditions are tractable or not. If we have the exact characterization of the set of MDM choice probabilities, we then can use it to reach our second goal, to develop nonparametric prediction and estimation procedures. So to study the research questions, here is our plan for this talk. Next, I will first introduce the marginal distribution model, MDM, followed by the exact characterization of MDM choice probabilities, that is the sufficient and necessary condition for the choice data to be representable by MDM. We then introduce the applications of using the exact characterization to do predictions for unseen assortment and estimate the best fitting choice probability to the choice data. And last, we will wrap up with conclusions. Before introducing MDM, let us introduce the random utility model RUM. The random utility models assume that each customer has a random utility on each product I, UI equals to UI plus epsilon I, when UI is the deterministic utility. Different customers have different epsilon. Since epsilon cannot be observed, it is assumed to be random with a non-joint distribution F. The key assumption in the random utility model is that each customer picks the product with the highest utility. Then the choice probability of product I in assortment S is the probability for the utility of product I greater than any other product in the assortment. The marginal distribution model can be viewed as the variance of the RUM. Given the deterministic utility news and the marginals of epsilons, MDM maximizes the expected utility by finding the joint distribution that is consistent with the given marginals. Then the choice probabilities are evaluated under the extremal distribution. It is proven in Natarajan et al. 2009, the marginal distribution formulation of MDM has an equivalent convex formulation, which results in one of the key advantages of this model, where the choice probabilities under MDM can be evaluated by solving a convex program. The convex program of MDM can be understood as follows. The utilities among products are separable. For each product I, the first term represents the deterministic utility, and the second term Ci can be viewed as the additive perturbation to the utility to revolve diversification. Here, I give a brief summary on RUM and MDM. We just discussed the details of the model assumptions of both models. For RUM, it is shown in Brock and Marshall 1960. The rank list model is equivalent to the random utility model. Rank list model assumes that each customer has a preference list sigma over products, and customer always chooses the most preferred option among the assortment. The description of the rank list model requires n factorial parameters. Given this characterization of RUM, the set of RUM representable choice probabilities can be described by the rank list model. MDM has an equivalent additive perturbation representation. Later, we will study the characterization of the set of MDM representable choice probabilities under such a formulation. So we just talk about the formulations of MDM and the efficiency of computing the choice probabilities under this model. There are other advantages of MDM. The tractability of MDM remains in more complex application settings like pricing, assortment planning, traffic equilibrium, and optimal transport. MDM is also known to be able to recreate the multinomial logit model with the perturbation functions Ci's are entropy functions and epsilons are identical exponential distributions. The asymmetric treatment of MDM with identical marginals has been studied by Freudenberg et al. 2015. Although a general specification of MDM does not impose restrictions on the marginal distributions, however, the estimation of MDM from data in the literature typically requires first committing to an appropriate parametric family to the marginals, and then the parameters are estimated from data using the maximum likelihood estimation. However, it's hard to fit the right parametric classes and is prone to suffering from underfitting and overfitting issue. Our goal is to develop non-parametric methods for estimation, allowing one to leverage the full modeling power of the MDM family. To study this problem, we begin with studying the characterization of the MDM representable choice probabilities across the given assortment collection. Equivalently, the necessary and sufficient conditions of the choice data to be representable by MDM. Similar studies have been done when considering RUM. The representable conditions for RUM has attracted attention from the economics for decades, back to 1960s. So what about MDM? What's the representable conditions for MDM? Is the representability check under MDM is tractable? Here's the answer for these questions. The choice data across a collection of assortment PS can be represented by MDM if and only if the set of conditions on the right-hand side are satisfied. These conditions are that exists a function lambda over the collection of assortments such that for a product I in a pair of assortment S and T, if the choice probability of product I in assortment S is less than the choice probability in T, then lambda S greater than lambda T. If this pair of choice probabilities are positive and identical, then lambda S equals to lambda T. You can understand the conditions with this simple example. The choice data can be represented by MDM if and only if we can find an order over assortments such that it is the reverse order of the choice probabilities of each product across different assortments. So unlike RUM to check the consistency over n factorial rankings, finding such a ranking over assortment under MDM is possible in polynomial time. And due to the representable conditions of MDM above, we have the following description of the set MDM representable choice probabilities for any given assortment collection. Here, let's see some numerical results of the characterization. The first experiment demonstrates that MDM has good representational power with a large number of products. In experiment 1, we investigate the representational power of MDM for a large number of products n equals to 1,000 and the number of assortment from 100 to 1,000 by randomly perturbed choice probabilities from an underlying MML model. We test the fraction of instances that can be represented by MDM, while the control parameter alpha is the fraction of choice probabilities being perturbed from MML. Different cases of perturbation are tested, that is 25%, 50%, 75%, and 100%. IRAN quickly becomes intractable as the number of products increases. It cannot run at this scale. Here we compare the performance between MML and MDM. As you can see from the figure, MML cannot represent the choice probabilities even for a small perturbation, while MDM shows good representational power and is much more robust than MML. The computation for this verification is efficient. Even for 1,000 products with 1,000 assortments, checking representable conditions of MDM takes less than 1 second. The second experiment is more about the checkability of MDM and its good representational power. In experiment 2, we compare the representational power and computational time of MDM and RUN for a small number of products n equals to 7 and number of assortment from 2 to 20. Other settings are the same as experiment 1. As you can see, MDM shows good representational power. Although RUN has a better representational power, this comes with a significant runtime cost, which is about 1 million times slower than checking MDM. So, okay, next we will talk about the applications of the MDM characterization. First, we started the predictions by using the exact characterization of MDM. Suppose that we want to make very new predictions for a new assortment A, which is unseen from the historical data. We begin with the assumption that the given choice data is representable by MDM. Using robust optimization and letting the choice probabilities of the new assortment together with the historical data being consistent with MDM characterization, we develop a data-driven approach to produce the worst-case estimate of the choice of the revenue. This approach has the following benefits. First, there is no need for parametric assumptions on the marginals in MDM. Second, if leverage the full modeling power of the MDM family. And third, the robust optimization procedure allows the data to automatically select the MDM based on the prediction task at hand. Replacing the infimum with supremum in the formulation, it produces the best case revenue for the unseen assortment. Together with the worst case estimate, we have the prediction interval for the revenue. To solve the revenue prediction problem, we developed a mixed-integer linear program which is generally applicable. Its size is polynomial in the number of assortment and the size of the assortment collection. Under structured collections, Such prediction tasks can be solved by solving polynomial-sized linear programs. Experiment 3 demonstrates that the proposed non-parametric data-driven approach for prediction can be beneficial, while there is a potential danger in imposing parametric assumptions on the model. In this experiment, we generate random instances with a product size 7 and a collection size from 20 to 80. And we use non-identical exponential distribution for the marginals to generate the underlying MDM choice probabilities. We then compare the prediction accuracy of two methods. First, for non-parametric MDM, we compute the worst case and best case revenue choice probabilities for the tested assortment in each instance. And second, consider an MDM with reshading the marginals to be identical exponential distributions, that is MML. We estimate the preference parameters in MML using maximum likelihood estimation, then use the estimators to predict revenue and choice probabilities for unseen assortment in each instance. In the figure, the blue dots are the grand truths, the green squares are the result by MML, while the red range are the result by the non-parametric MDM. The results show that the proposed non-parametric approach can correctly predict the true revenue or choice probabilities with the blue dots lies in the red range, while the MLE of the MML model can lead to very wrong prediction with the green squares far away from the blue dots. When more assortment are offered, the prediction and the non-parametric MDM becomes more accurate, while the prediction result under MML model become worse. Another application is the non-parametric estimation by using the MDM characterization. When the choice data is not fully consistent with MDM, we develop a limit of MDM to quantify the degree of inconsistency and finding the best fitting MDM choice probabilities. The limit of MDM is defined as the smallest loss that can obtain by approximating the best fitting MDM. A similar notion has been used to quantify the rationality loss for RUM. To solve the limits of MDM, we develop a generally equilibrable mixed integer convex program. If the loss function chosen to be one norm and the collection has special structures, the limit of MDM can be obtained by solving a linear program. In experiment 4, we use the limit loss to compare the exponential ability of MDM, RUM, and MML with product size 7 and number of assortments from 2 to 15. We examine the expected absolute deviation loss suffered by each model in fitting uniformly generated data instances. The figure reveals non-parametric choice models MDM and RUM have a better explanatory ability than the parametric model MML. Last, let me wrap up with conclusions. This is the first work to develop necessary and sufficient conditions for the set of choice probabilities to be representable by the marginal distribution model across any collection of assortment. The representable conditions can be tracked in polynomial time. By utilizing the exact characterization of MDM, we develop a non-parametric approach for revenue predictions for unseen assortments and a limit formulation that offers the best fit to the given choice data non-parametrically. The non-parametric approaches can get rid of the need of fixed distribution family in MDM beforehand and leverage the full modeling power of MDM and let the data select an MDM based on the prediction task and based on the task at hand. We develop mixed integer programs for non-parametric prediction and estimation, which are generally applicable. That's all for my talk. Thanks for listening. Below is the QR code to the full paper. If you have any question, please feel free to contact me via this email. Thank you.